Thanks, John. First of all, thanks for inviting me. Obviously, you know, AI and research is near and dear to my heart, an incredibly important topic, and I'm really happy to be here to talk about to kick this off. As John mentioned, I was thinking long and hard about this. There's a lot of things that I could talk about to this audience, and I really felt that maybe one of the most useful and interesting things would be lessons from industry. And so I'll give a little bit of background about myself to sort of lead into the fact that I took a 5-year leave of absence from the university to launch an AI and healthcare company. And there's just a lot of interesting lessons to be learned about applying AI in the real world that I hadn't thought of as an academic, and that might be interesting for this kind of group to think about. So a little bit about my background. So this will lead into talking about the company and some of these issues that I've learned. So I did my PhD at MIT back in the dark ages. I did machine learning. For those of us who've been in machine learning for some time, machine learning, artificial intelligence has gone through a lot of boom and bust cycles. So when I started my PhD in the late 80s, everybody thought that AI was going to take over the world. When I finished my PhD in the mid-90s, you literally could not get a job if you studied AI and machine learning, even from a place like MIT. It's just kind of crazy to think about it today, but that's what it's been like. And AI and ML has gone through boom and bust cycles since that point in time. I do really think that AI is here to stay, and I think the difference today than what it was like then is really threefold, right? And one is we have the data, tons and tons of data that's been collected digitally about every aspect of life that we did not have, back in the late 80s. We have compute, so we can operate on those data, and then we have much more sophisticated models like the transformer architectures, large language models, and so on and so forth. So I think it's really the combination of data, compute, and models which have really made the difference and turned the tide in terms of the widespread application of AI to almost all problems in the brain. So so I was a professor, have been a professor forever, since my earliest days. I was at Dartmouth for many years. I came here in 2003, so I've been at this institution since that point in time. I want to talk a little bit about, again, yes, I'm the Chief of Artificial Intelligence from the university. I'm not going to talk about that role necessarily. I do want to talk about lessons learned from industry. So let me sort of dive into that. So at some point in time, this is maybe going back 2010, I started doing some consulting for Mass General Brigham. So Mass General Brigham is by far the largest healthcare system in New England and one of the premier healthcare institutions in the entire world. And they really wanted to, they were very forward thinking. They really wanted to apply, data mining, artificial intelligence, machine learning to basically improve the efficiencies of their operations within healthcare. So this is not on the clinical side. So many academics are sort of focused on, how can we make clinical medicine better with artificial intelligence? This is on the administrative side. And that's maybe not nearly as sexy, but the thing is, healthcare is something like a $5 trillion industry, and it's something like 15 to 30% of healthcare dollars are spent on administrative tasks. Okay? So think about what that means. That is hundreds of billions to trillions of dollars that are spent, not on essentially providing healthcare to patients, but on administrative and back office operations. So their goal was to relieve that with science, if possible. And one of the things that they were very focused on at the time was relieving physician burden. And so, and if you are a physician, or if anybody here has doctors in their family, one of the real issues about being a doctor, especially in the United States, is all of the burdens that are outside of actually taking care of patients. So documentation, medical coding, pre-authorization, dealing with insurance companies, on and on and on. And these burdens have only increased over time for physicians. I know this personally. When my father is a doctor, he was a primary care physician. When I was a kid, he used to have that little black bag, and he would make house calls. I would sometimes go with him. By the time he retired from being a doctor, he said he spent more than half of his time dealing with insurance paperwork. More than 50%. And this is one of the reasons why he quit. He could have, I think he enjoyed doing medicine and would have kept practicing if it were not for this. this was the thing that that physicians at Mass General Brigham were facing, and that they wanted us to come in and help with. So and now I'm going to get into the company and some of the lessons learned, I promise. And so one of the things that that's part of this administrative burden and this hundreds of billions to trillions of dollars that's spent in the U.S. healthcare system is something called medical coding. So what is medical coding? So every time you go to see your doctor, documentation has to be written, but then your visit has to be paid for, typically through insurance. The insurance company does not want that documentation. That's not what they care about. They basically say, tell me what was done to the patient and why, and give it to me in a standard language that is used worldwide, something called CPT codes, which are the procedure codes. Like there's a procedure code for every single medical procedure that exists. There's like 50,000 of them. And then ICD codes that correspond to diagnoses. And there is a diagnosis for every single possible ailment or reason for a visit to the hospital that you can imagine. It's like 100,000 of them. Unbelievably specific. Things like hit by space debris. There's an ICD code for that. I kid you not. Okay? And so what is the medical coding burden? Somebody has to translate this medical documentation into these codes. It is oftentimes the doctor which has to do it. No doctor went to medical school to have to sit down with a manual of 50,000 CPT codes and 100,000 ICD codes to try to figure out which is the right one, where if they get it wrong, they will either be underpaid because they picked the wrong one, or they'll be accused of fraud because they picked the wrong one on the high side. Right? If doctors don't do it, then oftentimes you will have trained medical coding professionals that have to do it. People who actually go to just learn how to solve the medical coding task. And because medicine is so vast and there are so many of these codes, you have to have specialists. Like somebody will do medical coding just for chest CTs. Like that's all they do. They focus on that particular area as opposed to OBGYN or something else. So you need teams of these people. If you are a Mass General Brigham, you can hire these teams of people. If you are not, then you have to hire firms that do this. The medical coding workforce is sort of an aging population, and there's more of them leaving than are coming in. And so oftentimes this is outsourced to places like India. And what we've learned from my company is that the people in India who are doing this work are doctors. So instead of actually treating patients in India, they're actually doing medical coding for the United States. So this is really a great opportunity to apply machine learning to actually make things better. Relieve physician burden, get Indian doctors to treating Indian patients as opposed to doing coding for the United States, relieving physician burden, et cetera, et cetera. So this is the challenge that we took on. And so I ended up, started off as a consulting project, eventually, launched a startup, and at this point in time, I think we have like 130 employees, and we're working with most of the largest academic medical centers in the US. It's a different talk about what it means to go from academia to launching a company. I'd love to talk about that sometime. But I want to talk about the machine learning aspect. So what we do is essentially, we think of this as sort of a large-scale, multi-labeling problem. Like here's the input, it's a note. The output is a set of labels which correspond to the CPT codes and ICD codes that are appropriate for this particular task. Okay? So from an ML perspective, that seems simple. It's complicated in the sense that you have an incredibly large label space and it's a multi-label problem, but you can apply technology to solve this. What are the so as an academic, I thought, no problem, we'll go off and do this. Here are some of the challenges and the things that I sort of learned that were sort of interesting in doing this in the real world. So the first is, real world data is really, really, really messy. Okay. The kinds of data that we oftentimes deal with, like when I teach my machine learning class, the classic MNIST data set, ImageNet, UC Irvine, whatever. This is child's play in terms of complexity. Real world data is unbelievably messy. Messy and, like you're missing features, the labels are incorrect, the underlying documents are flawed, on and on and on. It's just, most of the time that I have spent in this company has been dealing with data issues as opposed to algorithmic issues. And I think this is something that we just don't focus on enough as academics. You know, like I'm a theoretical computer scientist. All of the work that I did for my PhD and since that point in time is developing new algorithms and tweaking algorithms. None of that, in some sense, was as nearly as interesting as if I had spent much more time learning how to deal with data. So that's the one thing. The other thing that this leads to is that there is huge amounts of inter-assessor disagreement for what the right answer is for this kinds of data. And this is true in this medical coding test, but this is true in many other tests that I've seen as well. And then when you're trying to deploy AI systems in the real world, this is an incredible challenge. Not only is it the case that the data that you're training from is incredibly noisy, like literally the inter-assessor disagreement rates for if you have a note, what are the right codes to associate it with it, something on the order of 30 to 40%. Inter-assessor disagreement rates. Okay? And then what we learn by talking to the customers that we're trying to deploy the to is they say, well, the industry standard is you have to be 90, there's one and only one right answer, and you have to get it 95% of the time. Okay? And that's just like the mantra, the Bible, from every single customer we've ever talked to. This is sort of the industry standard that they all adhere to, that they believe in, which is just being recorded, false. So, and then they will evaluate our systems and say, we disagree with you 30% of the time. Your system doesn't meet our 95% standard. And I'm going, yeah, but I can show you a study that your coders disagree with each other 30% of the time. So of course they're going to disagree with us 30% of the time, even if we have perfect answers. These are really difficult conversations to have with customers. And not only is it a challenge in terms of we're trying to train from this massively noisy data, but then how do you meaningfully assess it in the presence of this sort of thing? So real world data is incredibly messy. The second thing is real world systems are incredibly messy. And this is not just true in healthcare, but it's definitely true in healthcare. So most of the premier academic medical centers in the world, or in the US anyway, use a company called Epic. And there's sort of a running joke within our company, within the industry, is if you've seen one Epic installation, you've seen one Epic installation. So like basically every single place will install Epic in a different way, which makes it nearly impossible to develop a turnkey machine learning system that you can just plug in to solve a problem. And this is true certainly at this institution here at the university. I have lots of conversations with our CIO, and we have enormous numbers of disparate systems that have data in disparate formats that don't talk to each other. Things are messy. So these are real world problems that are way beyond just the algorithm problems that we have to deal with. The next thing is, and this is getting more to the point of things for you guys to think about, AI makes different mistakes than humans. And so then how do you judge when an AI system is good enough? Right? So this is something that we confronted for sure within our deployments. We would sit down and even in the presence of these inter-assessor disagreements, we came up with gold standard data sets by having multiple people evaluate when they disagreed, coming up with gold standard answers, blah, 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 blah. We could demonstrate that our systems were actually more accurate than the human beings on the task that we were applying it to. But we would make different mistakes than the people would make. And like, for instance, like at one point in time, our system was applying prostate codes to female patients. Okay? It was a mistake. We were making mistakes in aggregate at a much lower rate than the humans were making, but we were making a mistake that a human would never make. And so then there's just a trust issue, right? That they would look at this and they would say, your system is making a mistake that my medical coders would never make, therefore I can't trust your system, right? But we could show them the data that in fact our system would correct things, would never make the mistakes that your humans are making, similarly. But they understand the human mistakes and why these human mistakes are made. They don't understand the machine learning mistakes, and that becomes the problem, even if our overall error rates are far lower. Right? And so this is something that we just sort of had to learn and we had to deal with, that not all mistakes are created equal, and that there's something to be said about the kinds of mistakes that humans would make versus they don't are a different category. Like the other analogy I like to give, and maybe this is semi-controversial, but autonomous driving vehicles, right? You could get to the point where if they are at level 5 and they have far lower accident rates than human beings, you would say that's good in aggregate. But we look at an autonomous driving vehicle, and if they mistake a truck for a cloud, we say, well, a human being would never do that. I can't trust that system. But on the flip side, an autonomous vehicle will never get distracted by a screaming kid, won't spill their coffee, never drives while they're tired, never drives when they're inebriated, on and on and on. There's all kinds of mistakes that human beings would make that if an autonomous vehicle could speak, would say, I would never do that. So what does that mean in terms of us deploying AI systems in the real world for when we're sort of again the kinds of problems that we're doing, we're being judged by here's how humans would do them and the kinds of mistakes that they would make versus systems would. And then the final thing, and this just gets into human factors, and this is something that we really hadn't thought about. One of the areas that we tackled was trying to do automated medical coding for radiology. And in radiology, there's tons and tons of things which are just incredibly routine. If you go to a hospital, the first thing they're going to do is going to take a chest x-ray to see, if you come in with a cough, to see what's going on with your lungs. So there's like a bazillion, one view and two view chest x-rays, which are just like routine. And we could just automate all of those things. And we had heard from coders that in fact, that this is just an incredibly boring task for them. Chest x-ray after chest x-ray after chest x-ray. We said we can get rid of all those, and then we can, then there'll be hard cases that machine learning can't automate that'll be more interesting, so, some CT of the head or whatever. And then we deployed these systems, and we found out that, in fact, the unautomated cases that we were leaving for the coders to do were all the ones that effectively were hard and had high cognitive load. And the coders really missed having that mental break every once in a while where they just were given a simple one-view chest x-ray. They didn't have it, right? And so, we had to change our system to every once in a while, sneak in the one-view chest x-ray so that they would get a cognitive break. Right? And so, there's human factors that we have to think about when we deploy these tools. For me as a technologist, I would just say automate, 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 make the system better and better and better. But then you have to think about, well, if the tool that you're going to deploy is going to work with and alongside a human being, what is the right way to actually deploy that tool, right, in the presence of those human factors? And again, something that, again, when I was certainly a graduate student or a professor, I just didn't think about these things. You're just thinking about, how do I make my system more accurate? Anyway, so I'll stop there after some lessons learned and just leave it.